Welcome to the concept of inhibition and water treatment under the edges of chemical process utilities. Now, we have covered previously a concept about the mineral scale and deposits in water. We had a brief discussion about the concept of biofouling, colloidal fouling, corrosion related fouling, and we were discussing about the concept of inhibition and different aspects of inhibition. Now, in this particular lecture, we are going to discuss about the remaining part of types of inhibition. Then we will introduce the concept of microfiltration, ultrafiltration, nanofiltration, reverse osmosis. We were talking about the reverse osmosis quite frequently in the previous lectures. Mechanism of filtration, effects of various operating parameters which are important for the consideration. Now, let us have a discussion about the incorporation of various impurities. Now, impurities adsorbed on the crystalline interface can reduce the growth rate by reducing or hindering the movement of steps in crystal surface. Now, depending on the amount and strength of adsorption, impurities can be completely immobile to completely mobile on the crystal surface. So, that depends on the various scenarios. The strength of bonds between the lattice molecule and the impurity determines the relative mobility of the impurity in question. So, in general, strong adsorbing impurities are expected to have much greater effect on the growth rate of crystal than impurities that tend to be less strongly bound. Again, coming back to this step age adsorption, the step age adsorption suggests that adsorption of surfactant to the crystal surface can modify many aspects of crystal surface by lowering the interfacial energy between the solid and surrounding liquid. So, you know that every time all these phenomena, they are triggered by the interfacial energy or the surface energy. Now, impurities that adsorb the step age have similar effects, inhibiting the growth of steps by lowering the step age energy. The growth rate in the presence of inhibitors is usually assumed to be proportional to the number of active growth sites that are not blocked. So, these active growth sites play a very important role in this step age adsorption. The fraction of usually the growth sites that are blocked by the inhibitor is obtained using the Langmuir isotherm. It is a very common isotherm. The approach usually to describe the crystal growth inhibition is used by the researcher to model their rate data. The rate of crystal growth in the presence of inhibitor is obtained as Rho upon Rho minus I is equal to plus 1 plus K desorption upon K adsorption 1 upon Ci. Now, where R0 and Ri, they are the growth rates in the absence and presence of inhibitors respectively. Ci is the inhibitor concentration, and K adsorption or desorption, this can be considered as a measure of adsorption affinity of the inhibitor for the crystal surface. So, the rate law for crystal growth in the presence of inhibitor in its simplest form can be represented as nu I upon nu naught is equal to 1 minus Rc into theta eta maximum to the power half to the gross power half, where nu I and nu naught, they are the step velocities on the crystal face in the absence and presence of inhibitors. Rc is the critical radius of the 2D nucleus and correspond to the critical distance. Eta maximum, is the number of sites available for adsorption per unit area, and theta I is the coverage of adsorption active sites and is a function of inhibitor concentration in the solution. Now, suppression of calcium sulfate crystallization. Now, polyelectrolytes containing the carboxylic COOH groups such as carboxyl methyl cellulose CMC, allergenic acid, polymethylic acid and polyacrylic acid, they were the most active inhibitors due to their ability to preferentially adsorb on the active sites of gypsum crystal face. Other polyelectrolytes such as polyacrylamide, they had the little effect, and polycationic additives, they had no effect at all towards the suppression of crystal growth. Now, it was reported by various scientists that trace amount of phosphonates can stabilize the supersaturated calcium sulfate solution and lengthen the induction period before the onset of crystallization. So, researchers have concluded that the most efficient crystal growth inhibitor will be inhibitors that is structurally well fitted to the crystal lattice of the growing crystal. Maleic acid copolymer, polyacrylate, polyaspartic and polyglutaminic acids, acrylic polymers, polystyrene alternate maleic acids, tartarates, diisooctyl sulfosuccinate, uric acid, polysodium styrene sulfonates. It was also reported that the ranking of polymeric inhibition can be written as polyacrylate, polyasparates, polyglutamate. Now, let us have an introduction about the various microfiltration tools. Now, membrane separation technology, they are based on the process that is known as the cross-flow filtration, which allows the continuous processing of liquid streams. So, in this particular process, the bulk solution flows over and parallel to the membrane surface, and because the liquid is pressurized, it adopts a force, water is forced through the membrane. The turbulent flow of the bulk solution over the surface, it minimizes the accumulation of particulate matter. Now, here you see this the conventional filtration. Here this is membrane, you are supplying the feed over here and filtrate is coming out. Where is this is the conventional filtration, where this is the cross flow filtration, where feed is supplied and concentrate is coming out and the permeate over here. So, this is your filtering media or filtration media. So, microfiltration is utilized to remove the submicron suspended material on continuous basis. The size ranges from approximately 0.01 to 1 micron or 100 to 10,000 angstrom. Now, by definition, microfiltration does not remove the dissolved materials. Now, you can see that the different specification of microfiltration lies that 0.1 to 3 bar, 0.1 to 5 micrometer. Similarly, ultrafiltration 2 to 10 bar with the pressure applicability and 20 nanometer to 0.1 micrometer. Nanofiltration 5 to 30 bar greater than 1 nanometer, and reverse osmosis 10 to 100 bar 0.1 to 1 m, that is very close. Now, let us have a brief discussion about ultrafiltration. Now, ultrafiltration is the membrane process that removes dissolved non-ionic solutes, typically organic material or sometimes referred as macromolecules. Ultrafiltration membranes, they are usually rated by the molecular weight cutoff and sometimes referred as MWCO, the maximum molecular weight of the compound that will pass through the membrane pores into the permeate stream. So, ultrafiltration pore size, they are usually smaller than 0.01 micron or 100 angstrom in size. The microfiltration and ultrafiltration separate contaminants on the basis of sieving process, and that is any contaminant too large to pass through the pore is rejected and exists in the concentration stream, which we have showed in earlier photograph. Now let us have a discussion about the nanofiltration. The nanofiltration can be considered loose reverse osmosis. It rejects the dissolved ionic contaminants but to a lesser degree than reverse osmosis. Nanofiltration membrane, they rejects a higher percentage of multivalent salts than monovalent salt, and that is 99% versus 20%. These membranes have molecular weight cutoff for nanoionic solids below 1000 Dalton. Let us have a discussion about the reverse osmosis. The reverse osmosis produces the highest quality permeate of any pressure driven membrane technology. Certain polymers will reject over 99% of all ionic solids and have molecular weight cutoff in the range of 50 to 100 Dalton. The phenomena of osmosis occurs when pure water flows from dilute saline solution through a membrane into higher concentration saline solution. A semi-permeable membrane is usually placed between the two compartments like this. These are the compartments. A semi-permeable sometimes referred as the membrane is permeable to some species and not permeable to others, or we can say it's a very selective one. Now assume that this membrane is permeable to water but not to salt. So then place a salt solution in one compartment and pure water in the other compartment. The membrane will allow water to permeate through it to either side, but salt cannot pass through the membrane. Now, as a fundamental rule of nature, the system will try to reach the equilibrium. It is quite obvious that because one compartment has the higher concentration and other is lower concentration, so they will try to match the equilibrium. And that is, it will try to reach the same concentration on both the sides of the membrane. The only possible way to reach equilibrium is for water to pass from pure water compartment to the salt containing compartment to dilute the salt solution. Now thereby the osmosis can cause a rise in the height of the salt solution. Now this height will increase until the pressure of the column of the water, that is the salt solution, is so high that the force to this water column stops the water flow. Now the equilibrium point of view, this water column height in terms of water pressure against the membrane is called the osmotic pressure. It is a very common phenomena. Now if a force is applied to this column of water, the direction, again I am reproducing the rough figure. So the direction of the water flow through the membrane can be reversed. So if we apply the force to this column, the direction will be reversed, direction can be reversed. Now this is the basis of the term reverse osmosis. Now this is the reverse flow this reverse flow produces a pure water from the salt solution, since the membrane is not permeable to salt. So it prevents the flow of salt to the other column. The nanofiltration membrane is not a complete barrier to dissolved solid. So depending upon the type of salt and the type of membrane, the salt permeability may be low or high. Now, if salt permeability is low, the osmotic pressure difference between the two compartments may become almost as high as in reverse osmosis. On the other hand, a high salt permeability of the membrane would not allow the salt concentration in the two compartments to remain very different. Therefore, the osmotic pressure plays a minor role if the salt permeability is high. Now, this is a very useful information in designing all these reverse osmosis concepts. Now, let us have a discussion about the mechanism of nanofiltration and reverse osmosis. So, in practice, the reverse osmosis and nanofiltration are applied as a cross flow filtration, which we had already discussed. The simplified process is shown in this one. Here you are supplying the feed water. This is the feed pump, and this is our semi-permeable membrane, and this wall, and this here we are passing through the concentration. Now, this is a pressure vessel plus membrane element. So, this is my pressure vessel. So, this feed water comes out through this feed pump and permeate comes out over here, and the concentrate goes in this particular direction. Now, with a high pressure pump, the feed water continuously pumped at elevated pressure to the membrane system. Now, within the membrane system, the feed water will be split into a low saline and or purified product, that is called the permeate, and a high saline or concentrated brine, that is called the concentrate or reject. A flow regulating valve, usually called the concentrate valve, controls the percentage of feed water that is going to the concentrate stream and the permeate which will obtain from the feed. Now, recovery. The percentage of membrane system feed water usually that emerges from the system as a product water or permeate. Now, membrane system design is usually based on expected feed water quality, and recovery is defined through initial adjustment of valves on the concentrate system. Now, recovery is often fixed at the highest level that maximizes the permeate flow while preventing precipitation of supersaturated salts within the membrane system. The rejection, that is called the percentage of solute concentration removed from the system feed water by the membrane. So, in reverse osmosis, the high rejection of total dissolved solids, sometimes referred as TDS, is important, while in nanofiltration, the solute of interest are specific, that is the low rejection for hardness and high rejection for organic matter. The passage, this is the opposite to the rejection. The passage is the percentage of dissolved constituents, that is the contaminants in the feed water allowed to pass through the membrane. Permeate, the purified product water produced by membrane system. The flow, the feed flow of is the rate of feed water introduced to the membrane element or membrane system, usually measured in gallon per minute or any unit applicable to, or sometimes cubic meter per hour. The concentrate flow is the rate of flow of non-permeated feed water that exists the membrane element or membrane system. Now, this concentrate contains most of the dissolved constituents originally carried into the element or into the system from the feed source. Now, it is usually measured in gallon per minute or cubic meter per hour. Let us have define the flux. The flux, the rate of permeate transported per unit of membrane area, and usually measured in the gallon per square foot per day GFD or liters per square meter an hour. Now there are certain factors affecting the nanofiltration and reverse osmosis. The permeate flux and salt rejection, they are the key performance parameter of reverse osmosis or nanofiltration process. Now, under a specific reference condition, flux and rejection are intrinsic properties of membrane performance. The flux and rejection of membrane system are mainly influenced by various parameters like pressure, temperature, recovery, feed water salt, concentration, the pH, etc. So, these are the controlling parameters. Now, let us have a discussion about the pressure. With increasing the effective feed pressure, the permeate TDS will decrease while the permeate flux will increase as shown in this particular figure. Now, this is the pressure and you see that permeate flux is increasing and salt rejection. Now, because reverse osmosis membrane are imperfect barriers to dissolve the salt in feed water, there is always some salt passage through the membrane. Now, as feed water pressure is increased, this salt passage increasingly overcome as water is pushed through the membrane at a faster rate than the salt can be transported. However, there is a upper limit to the amount of salt that can be excluded via increasing feed water pressure. Now, as the plateau of the salt rejection curve indicates, above a certain percentage, above a certain pressure level, the salt rejection no longer increases. You can see over here. And some salt flow remain coupled with water flowing through the membrane. Now, let us discuss about the effect of temperature. Now, if temperature increases and all other parameters are kept constant, the permeate flux and salt passage will increase. Now, you can see in this particular figure, we are keeping the temperature increasing, then the permeate flux, you can see that is the incremental trend in the permeate flux and salt rejection slightly on the lower arm. Now, we are maintaining the constant pressure and constant flux. So, increased feed water temperature also results in lower salt rejection or high salt passage. This is due to a higher diffusion rate for salt through the membrane. The ability of a membrane to tolerate elevated temperatures increases operating latitude and is also important during cleaning operation because it permits use of a stronger, faster cleaning process. Now, this you can illustrate by the comparison of the pH and temperature ranges of thin film composites and cellulose acetate membranes. Let us have a discuss about the effect of recovery. Now, you can see in the figure, this figure, the reverse osmosis occurs when the natural osmotic pressure between the dilute solution and a concentrated solution is reversed through the application of feed water pressure. So, if percentage recovery is increased and that means the feed water pressure remains constant, the salt in the residual feed becomes more concentrated and the natural osmotic pressure will increase until it is as high as applied feed pressure. So, this can negate the driving effect of feed pressure, slowing or halting the reverse osmosis process and causing the permeate flux and salt rejection to decrease and even stop. So, the maximum percent recovery possible in any reverse osmosis system usually depends not on the limiting osmotic pressure, but on the concentration of salts present in the feed water and their tendency to precipitate on the membrane surface as mineral scale. So, the most common sparingly soluble salts are calcium carbonate, sometimes called as limestone, calcium sulfate, called as gypsum, and silica. The chemical treatment of feed water can be used to inhibit the mineral scaling. In this particular chapter, we had discussed about the various aspects of inhibition. We had discussed about the different aspects of microfiltration, ultrafiltration, reverse osmosis, etc. And if you wish to have a further reading, then we have enlisted couple of references for your convenience. Thank you very much.